So that was the brief overview of the structure that hopefully you should be able to follow through. Let's go into the first topic for today, which is, as I said, motion of a single aerosol in a fluid. Again, let me know if my handwriting is outside the screen. Again, I tend to use both particle and particulate. I personally like the word particulate a little bit more because the simulations that we run and we are going to run in this course, we model them as inert particles. On the other hand, it is understood that they are made of liquid. So I like the word particulate more than particle just to carry that sense that it is still liquid particles. Now, as I said, we want to first develop a mathematical understanding of the motion of a single particle or a particulate. Now, first, let's think about what we can achieve from those mathematics and what are the assumptions that would go into developing that mathematics. The context over here is we want to develop an understanding of aerosol dynamics within a complex domain. Like the human respiratory tract. And we are going to model the deposition mechanics within the tract, we are going to simulate the process. But we are going to first start with it being a single particle motion. So much of the aerosol mechanics can be theorized through understanding the motion of a single particle. And to understand the motion of a single particle, we need to figure out the forces, the trajectories of that particle. So we get the trajectories from the corresponding equation of motion. So the idea is to be able to develop the equation of motion for that particle. So forces and equations governing the motion of a single particle moving through a fluid. And while developing those equations, we are going to apply the appropriate assumptions in terms of different aspects, like what kind of Reynolds numbers, Stokes numbers, Rolle numbers we may expect in those domains. And that particle will be a small, rigid, single particle moving through air. So every time I say the word fluid, in this case, because we are trying to study breathing and inhaled particle transport through our airway, that ambient fluid is going to be air. So the problems that we are going to solve, we are going to use the material properties for air. Now, while developing the equations, the two main assumptions that we are going to use would be this. Number one, the particles are going to be assumed to be spherical, which is a good assumption most of the times. But if you look at recent literature, people are also looking at what happens if they are non-spherical. The good thing is, in terms of the regional deposition trends, even if you consider them to be non-spherical versus spherical, it does not make much difference. So if you are trying to apply your fluid mechanics knowledge into understanding infection mechanics, into understanding targeted drug delivery, it doesn't make that much of a difference. So that's number one assumption. The particles are going to be assumed spherical. Number two, we are going to assume that the density of these particles, the material density, is much, much higher than the density of the ambient fluid or the ambient air. So let me write those down. So the two main assumptions in respiratory aerosol science. Number one, the particle is assumed spherical. And as I said, this, in terms of when we are trying to apply the knowledge to a practical problem, this is a fairly reasonable assumption. So this is usually reasonable. Number two, the density of the particles is much, much greater than the density of the fluid, which in this case is air. Now, this also is quite reasonable most of the times. Because if you think about drug delivery, what do you think the density of those particles are for drugs? For nasal sprays, nebulized sprays? Slightly above water. Most of the times it's very close to water. So 1000 kg per cubic meter, and what is the density for air? Yeah. So it's much, much better than the density of air. What about infection transmission? What about those particles? So if so how do we infect others? So we eject this particulates that are sheared away from our mucus. Initially, if you think about the fluids in our airway, it's mostly water, and then the moment it goes out into the air, it undergoes some environmental dehydration. It actually loses the water, becomes even denser than what it was inside our airway. So it is, of course, going to be much, much dense than the air. But can you think about a situation where this assumption might be sort of questionable? That the density of the particles is not probably much, much better than the density of air. So someone, yeah, go ahead. Yeah. So someone said that aerosols are things that stay airborne, right? Rather, it's more accurate to say that after those ejecta particles lose all the water, those gradients, which are the single virus particles, they stay airborne for hours. Now, those variants are not spherical, so forgetting the first assumption, they could be much, much light. And the density of those variants could be comparable to that of the air. So that caveat is still there if we are trying to think about a single variant. In our course, or for that matter for most of these kind of inhalation studies, we assume that those variants are embedded in liquid particulates, in which case the density of those whole particles could be assumed to be much better than that of air. So hopefully I'm going to comment on this later on in this week. We'll be going to the infection transmission part of the course, but for now we're going to assume that rho P is much better than rho fluid. So let me just write down the comments here, but exceptions could be there. For example, micron scale, and for that matter, sub-micron scale, airborne virus nuclei. And we'll comment on this later on. However, for our purposes, for now, we are going to assume that typically, if you track the order of magnitude difference, rho vertical is 10 to the power of 3 of the rho fluid. So as a result, we do benefit in terms of the forces from the fluid that we need to consider in our equations of motion for those particles. So which force do you think should be considered? What is the main force contributed by the fluid? Huh?
Van der Waals forces.
No. Van der Waals forces is the molecular, intermolecular. Huh? That's a field force. I'm talking about the fluid force. What is the main force that is used? Drag. Drag is the main force that is going to dominate over all the other forces. So the result of assumption 2 is drag force on the particle is much larger than all the other fluid forces that may act on it. I mean, they're still there, but with the equation we can ignore their overall effects. Okay? But then again, we have left out this caveat, so let's quickly take a qualitative note of what forces could have been there before we go into the actual equation. So however, if the rho particle is of the same order as the rho of fluid, several fluid forces like Magnus force. So this is the lift force that is generated from a surrounding fluid field on a spinning particle. Bassett force, pressure forces.
Sound looks out of the slide. How it's
if I remove the page, it does focus a little bit. Facts and correction. Virtual mass effects. Would become prominent. Now, based on your problem that you're trying to solve, you might have to include some of these effects and perhaps some I have not listed here. In the simulations that we are going to run, along with the regular drag and the gravity force is still there, it's a field force. I do include the Safman lift force because Safman lift force is specific for particles that are very small and they act transverse to the direction of the particles. So since we are trying to track radial drug delivery, I do include that lift force into the numerics. But I'm not going to include that in the equations that I'm going to develop because its contribution is anyways very negligible compared to the drag force. So including all this is fine, but that would make the analysis much more challenging. So, for our purposes, let's hold on to assumption 1, particle is spherical, and assumption 2.
Sir, what is the Magnus force and basic force?
So the Magnus force is on particles that are spinning, it's a lift force.
So, like, have you studied the potential flow chapter? In that, it is discussed like there is a uniform flow, then like a cylinder is rotating, then there will be like that kind of force. So,
And yeah, if you want to discuss details.
you can maybe after this session, the questions around it.
And you can just look them up as well, because knowing these forces, what they qualitatively mean, is important, especially when you are trying to solve an unknown, unsolved problem and you don't really know what are the different effects that could be pushed. For now, we don't need to worry about them as long as the particle density is much higher than the density of air. So with this, let's go into the main dominant force that we do need to encounter, which is the drag force. So, assuming the drag force to be the only non-negligible fluid force on the particle, and the only body force is from gravity, we can write down this very basic equation of motion, which is m dv dt is mg plus f drag. So I'm going to use that over bar on each of these terms if I'm inclined to a vector quantity. So this is the equation of motion. Of a single particle. And something that we have known since our high school days. And whatever else would follow would be based on these equations and how we can ignore or place assumptions on the different terms. Now to solve this equation, we do need to solve this equation because we want to get the particle trajectory, right? So we need to solve for the velocity, and integrating the velocity, we get the trajectory of the particle. So to solve this equation, equation for v as a function of the time t, we must determine the drag force. Now to determine the drag force, what do we first need? We need to know something called drag coefficient, which I'm sure you have encountered before as well. So therefore, now the drag coefficient CD is F drag divided by half rho fluid So what is that V rel? It is the relative velocity of the particle with respect to the free stream velocity of the ambient fluid. And area is the cross-sectional area of the particle. So here, A is the cross-sectional area of the spherical particle. So if D is the diameter, so pi d square over 4. And for that matter, if we had ignored the first assumption, this is where things start to get complex. We need to know the profile of the particle if it is indeed non-spherical. The V relative is V bar minus V fluid. We are solving for V, which is the velocity of the particle, and the free stream velocity is V fluid. Okay, now with this being true, this is the CD, fine. What is the direction of the drag force? The direction of the drag force is opposite to the relative motion of the particle. So if whatever the particle is doing with respect to the fluid, the drag force will be directed opposite to it. So let's see what is the vectorial form for the drag force. The drag force acts opposite to the velocity of the particle relative to the fluid. So let's write the drag force down hence. So F drag is minus half rho fluid V well squared pi d square over 4 Ct, the unit vector for that relative velocity. So write the unit vector V rel is okay, the negative sign accounts for the fact that it is directed opposite to the motion of the particle. Okay, so that being true, this CD that is there in this formalism for the drag force depends on the Reynolds number of the fluid. So let's see what that dependence is like. Here, the drag coefficient CD depends on the particle Reynolds number such that so Reynolds number is this. Let me correct, it's the Reynolds. So when I would write RE, I would imply to the Reynolds number of the particle. So that's why I'm trying to take this V rel as the velocity in the Reynolds number formalism. This viscosity would be the viscosity for the fluid. So this is the kinematic viscosity. Which would be mu over rho of the fluid. Now, to connect this Reynolds number with the crack coefficient C, there are some empirical relations. So, to connect RE and CD, there are empirical relations. For example, CD is 24, 1 plus 0.15 RE to the power 0.687.
How much is the size of these particles?
These are micron scale. The size could be anywhere between 0.1 to 500 micron. So this is the most generic empirical relation, but based on the size of the particle. So, but most particles that are inhaled have very small diameters t and low velocities v well. So which tells us that RE is small for these particles. Therefore, we can assume CD to be 24 over RE. Now, in terms of the size of the particles, as I said, it could be from 0.1 to around 500 microns. Now, on the larger size of the spectrum, 500 microns, those are the particles that are relevant for drug delivery. On the smaller end of the spectrum, those are the particles that are relevant for infection transmission. For typical nasal sprays, the median diameter is anywhere between 30-40 microns, but they can go as high as 500. Okay, so we are going to use this expression for CD, 24 over RE, and this is for RE less than 0.1, which gives a CD within 0.1% error. Okay? So now I'm going to plug this CD into the formulation that we had for the F drag. By the way, I use this acronym PTO a lot, which as Indians we know that it is turnover. So once I ask so I've been using this for a while in my classes that I teach at SJSU, and once I asked my American students, do you guys know what is PTO? Can you guess what they thought it is? Paid time off. So they thought that I'm giving them paid time off after every single page if there is one space. So I had to tell them that no, we are referring to our former British masters that please turn over the page. Okay, so let's call this equation 3, and the equation numbers are going to be difficult to keep track of eventually, but since we are going to connect different equations together, but this is equation 3 for now. So F drag is that equation, and we are going to use that. So therefore, from equation 3, the F drag is minus half rho fluid V well squared by d squared over 4, 24 over RE, so I'm breaking the Reynolds number up. Kinematic viscosity divided by v rel times t, and the unit vector in for v rel. So let's simplify this a little bit. So we have 2, 4, so this becomes 3. We have 1 v relative over here, so that cancels the square. And what else? The t gets cancelled here. So f drag is this 3, so minus 3 pi. This nu could be broken up as well, so if I do that, nu d v minus v fluid, I'm writing the, I'm combining this vrel with the unit vector for vrel to write it in the vector form, and I've used mu as the row fluid times. So we have seen this equation a lot of times in fluid mechanics. What is the name of this equation? Stokes law. So this is valid for particle diameters that is greater than the mean free molecular path. So in air, that mean free molecular path is, anyone wants to take a guess how small that could be? It is 0.067 micron. So when I said 0.1 micron is probably the smallest particle that we typically need to consider, we can still have this assumption true. So in air, at typical breathing conditions, this mean free path distance is 0.07 micron, actually 0.067. So this gives the Stokes law, but before we start solving problems, let's think about a few other effects. We can have a particle that is not really moving, it is trying to settle in the fluid, and that leads to the regime called settling mechanics. So we are going to study that. And then sometimes the particles are trying to move with respect to the fluid. They are moving fast, and therein comes the concept of the inertial dominance of the particle's motion. So we are going to look at that kind of inertial mechanics as well, which leads to inertial sedimentation. So both gravitational sedimentation, settling, as well as inertial impaction. So let's try to derive the equations for that. In terms of our timeline, let's continue till noon, and I'm going to ask you guys if you want to continue a bit more. But let's try to cover most of the mathematics that I wanted to cover by end of today. Any questions before I move on?
Noon implies 12, right? Noon implies 12 or 12:30?
Noon implies 12 for me.
Okay, so noon implies 12. So, like,
But if you want to continue further, we can do that.
yeah. Otherwise, we'll meet at 2. But try to be like finish your lunch before assemble there by 2
Okay, so from here, we are going to go into the concept of settling velocity. Do keep track of the equation numbers before we move further. So this is going to be equation 4, which we are going to use later on again. So particle in stationary air will settle under gravity and reach a terminal velocity quite rapidly. And this process has a specific name, it is called sedimentation. So if we are to develop the equation for this process, the process of sedimentation mechanics, we are going to again start from the very basic equation of motion that we started out with before. So since the velocity of a particle does not change once it reaches the terminal velocity, does not change once it reaches the settling velocity. In the equation, which is m dv dt is mg plus f drag, we can ignore this particular term. That velocity, the change of velocity is 0. Therefore, this is a vector equation. But if we want to think about the individual terms in this force equation as in terms of the scalar contributions, we can write for equilibrium mg would be equal to the F drag. The vertical force must balance the gravity force. So now we can try to use the formulation for the drag force that we had developed before. So let's see what happens if we do that. So assuming the Reynolds number to be much small. Again, even I got confused with the Reynolds number. This is not the Reynolds number of the fluid. This is the Reynolds number that we are talking about of the particle. So this is the particle Reynolds number. And the air velocity V fluid to be 0 because we have started out saying that the particle is moving through stationary air. So we can apply that into the equation that we have derived before. So this is stationary air. Therefore, equation 4 reduces to. So what is equation 4? Equation 4 is this particular form. So the F drag. So let's apply this directly over here. So equation 4, F drag becomes 3 pi mu d V settling. So V settling is the velocity of the particle that we had as V before, but now we are calling it as V settling. So this I'm going to call as equation 6, with this being equation 5. So the minus sign, I am ignoring that for now because I am trying to quantify the drag force. We are no longer concerned with what direction they are. We have to understand that it is opposite to the direction of motion of the particle. Yes?
So could you please tell how important is the added mass force while determining the velocity? If we see the vector equation, is it always negligible when we talk about added mass force?
It is not always negligible. What we are assuming is these particles at this length scale, their densities being much greater than the density of the surrounding fluid.
Yes.
We can ignore that mass effect, and that's what we are doing.
As well as basicity.
So let's now try to apply this F drag into equation 5 where we have the gravity force. So therefore, in equation 5, we have mg as 3 pi mu d times v settling, and this mg is rho particle 4 by 3 pi d cube over 8 times g is 3 pi mu d v settling. If I miss any term, because I'm going to do it by hand, just shout out if I miss anything. So rho particle 4 by 3 pi d cube over 8 times g. Okay, so let's see what we can cancel over here. So this goes out, and rho particle, so d cube over 6 times g is 3 mu d resettling, or resettling is rho particle, this d would make it square, so d square g, this 3 goes down, so 18 mu. So this gives us the settling velocity, and this particular structure appears elsewhere as well, as we are going to see later on. So this is the settling velocity of a spherical particle under gravity. And again, what were the assumptions here? The Reynolds number of the particle is much, much small. The particle size is much, much greater than the main free path in the fluid motion. And both the assumptions are true for inhaled aerosols. So again, this assumes that RE is much, much smaller, and the d of the particle is much greater than the main free path. And this is true for most inhaled aerosols. Okay, so now we have a formula for the settling velocity. Let's solve a problem before we move further. By the way, in terms of solving problems, do you guys have calculator on you guys?
No, next class onwards, maybe at least use the mobile.
Using mobile would be tricky, but yeah, do try to build the calculators from the next session onwards. So I have the numbers here, so I will use.
You have calculators, most of them.
But if you do have calculators,
Try to read from BTEC things answers.
yeah, you can tell me if any of my calculations are not correct, because I just prepared these notes before coming here. Okay, so this example is on drug delivery, by the way. So evaluate
Slightly change
evaluate the Reynolds number of a 10 micron diameter spherical budesonide powder particle settling in room temperature air. we need to know some of the material properties, but as a side note, let me just point out what this means, because this is not in our territory of knowledge for us mechanicians. So this is a drug which is used for asthma treatment. So the drug used in treating asthma. Now let's look at the material properties. This compound's material density is, so the specific gravity is 1.26. That's 1.26 times 1000. The viscosity of air is what you need to know, is 1.8 times 10 to the power of minus 5 kg per meter second, and the density of air is 1.2 kg per cubic meter. So we can directly apply the formula that we had derived. The particle settling in stationary air, we have V settling is rho P, V square G over 18 mu. So let's put in the numbers here. So the rho P is 1.26 times 1000 kg per cubic meter. The D is given as 10 micron. So 10 times 10 to the power of minus 6 meter squared. And G is divided by 18. Mu is given 1.8 times 10 to the power of minus 5 kg per meter second. I have double checked the dimension, but it should be fine if you do the calculation. If you had calculators, anyone has calculator here? So do the calculation, because I want my work to be double checked as well, because my answer will be wrong. What I have here is 3.815 times 10 to the power of minus 3 meters per second, or 3.815 meters. So if that is the velocity of the particle of settling, then we can directly put it into the Reynolds number formulation to get the Reynolds number, which is what this problem had asked us to find. So therefore, the particle Reynolds number is V settling T over mu by rho air. So V settling is 3.815 times 10 to the power minus 3 meters per second. D is 10 micron. Mu is 1.8 times 10 to the power of minus 5 kg per meter second, divided by the density of air is 1.2 kg per cubic meter. Again, you should double check the dimensions, but I'm pretty sure they are fine over here. So this number should come to 0.002543 if you double check the number. So folks who don't have calculator, please.
So when you are calculating the Reynolds number of the particle,
Yeah.
we are considering the viscosity and the density of the
Yeah.
surrounding medium,
Yeah.
not the particle fluid.
And that's what threw me off while I was preparing the material, because That is what is going to control the motion of the particle, not the properties of the particle as such, beyond the density. Because it's non-deformable, because it is inert. And that point, I think I have some material on that as well, because if you do think about the viscosity of the particle, there is a particular term that we have already used that gets revised. That term is the drag coefficient. So I have some notes on that as well, which I think we are going to touch upon today at some point. So this is 0.0025, which is much less than 1, which tells us that the assumption that we had started out with is still valid. So therefore, we have used the settling velocity formalism quite justifiably. Yeah, so if the numbers change once you do the double checking of the numbers, just let me know. Questions? So the next point is actually connecting back to what you just mentioned. Until now, we are assuming the viscosity of the surrounding fluid, right? While getting all these numbers. In other words, we are assuming these particles to be solid and inert. What if they are not? What if we do need to consider the viscosity? So what gets corrected in our equation? So let's take a look at that. So the formalisms until now were for solid spherical particles. But if they're not solid, the fluid wrapping the particle around the particles can create an effect called internal circulation. Anyone has any experience with that kind of mechanics? Circulation inside droplets. So, so that effect does change the overall equation. So let's take a quick look at that. So however, if the particle is not solid, but is instead a liquid particulate, it is possible for the relative motion of air flowing past the particulate to induce internal circulation. So that would change the overall effect of the drag. So let's take a look at that because of this internal circulation. But before that, since we are trying to approach respiratory biomechanics over here, can you think about a particular situation where this would be valid, or where this particular nuance could be very critical to the physiological function of that process? That the particles' internal circulation of the fluid material inside is very relevant. It actually happens in the alveolar sacs. So as we inhale air in, when the particles go to that kind of length scale, there the internal circulation of the particles is quite critical to the exchange that is happening gaseous, extremely everything. So there's a group in Israel. I'm going to touch upon one of his papers later on. They are looking at that effect. So basically, they are 3D printing the entire lower airway branch model. They don't consider it to be a 3D structure anymore. They're basically including certain layers of branching, certain generation of branching, a 2D 3D printed model, but they're looking at that kind of internal circulation in the particulates that are in the very fine particle channels. Okay, so if we do have this kind of liquid particulates where this effect is prominent, let's see what happens to the settling velocity as a result. So settling velocity for liquid particulates the internal circulation lowers the drag force effect and increases the settling velocity compared to that of the solid spherical particle that we are studying until now. So compared to a solid sphere, of same size and density. And along with this internal circulation, if you think about liquid particulates that have some internal contaminants, their motion can make the process even more challenging to track. So note the surface impurities in liquid particulates can make the mechanics quite challenging. Okay, now let's focusing back on what changes to the drag force because of this effect. This equation was derived by Hadamard and Rimsky. So F drag is 3 pi mu d v rel times 1 plus 2 mu of air by 3 mu of the particulate divided by 1 plus mu of air by mu of the particulate. Now if you think about this correcting cofactor that is coming in, if you do put in the numbers, you will see that in our purpose, it becomes close to 0.994. So it is okay to ignore it most of the times. But this is what happens if you do want to include the viscosity of the particulate material into your equation. So this factor So this is the factor that is extra for water droplets. In air, it is close to 0.994. So the internal circulation effect could be negligible for the problems that we are going to study. Noon time. Do you want to continue or stop for now? Okay.
Not saying.
Even
So
here
stop for now, like then again we will meet at 2. But you can like ask him regarding the registration if there is any query.
Okay, let's stop for now. Your professor wants me to stop for now, so let's stop.
Let's go slow today. Pick it up on the coming 2 days, 3 days.
Any questions before we stop now? Okay, so when do we meet again?
2 here will be.